Hello, radical scientists. So here we go with the week 2's level 3 assignment, applying Ohm's law, and again specifically looking at part 2. I'm actually going to touch on two problems, the number 4 and number 5, really briefly. I'm going to solve for 5, but for number 4, a quick disclaimer. My apologies, there's a mistake here that might have really affected some of what you resolved for. The question should read, we have two resistors, not two 10 ohm resistors. The first resistor is a 15 ohm, the second resistor is 24. There are no third and fourth ones. That 10 ohms is just something I forgot to erase, so my apologies for the confusion. And for the fifth one, we're going to go ahead and solve for Ohm's law, an unknown variable, but using different types of structures. I'll go more into detail as to how exactly this looks out when we start applying multiple resistors. But you have to remember that this second part, once again, is having practice with using that relationship. Current is equal to voltage over resistance in different situations as it applies, and sometimes we have to modify it for different things. But at the end of the day, that is what is going to help us ultimately solve for an unknown variable. So with that, here we go. All right, here we go, folks. And here I'm going to go and once again remind us that there's a little no-no here. I apologize for including that 10 ohm. You can erase it. We're looking for two resistors, and you'll be able to solve for this using honestly a simpler way that we're going to solve for this video's walkthrough of question number 5. How many 10 ohm resistors? So all our resistors are 10 ohms. How many 10 ohm resistors must be connected in parallel to generate 5.0 amps of current from a 12.5 volt battery? The resistances are unknown. We know our current and we know our voltage. What is the resistance? And this really comes understanding that what we're looking at here, this different equation that we looked into for parallel resistors, is not an alternative to Ohm's law. Once again, where, whoops, I was going to do it again. Current is equal to voltage over resistance. This relationship is still true. What is different is that with different resistors, we now have to use a really quick kind of amendment, what have you, some type of different modification to solve now for a resistance total, the total resistance that relates to all of these different numbers, right? And once again, we can quickly solve for this just given what we already have, right? We have our current and we have our voltage. I'm gonna go ahead and put this in here, right? Our current being 5.0 amps, our voltage being 12.5 volts, and lastly our RT being this unknown variable. If we multiply both sides by RT, right, this should cancel these out to 1. Multiply this side by RT as well. We have to do same thing to both sides, and we divide. We're gonna do 2 for 1 step here. Both sides by 5 amps over here, right? So I'm gonna extend this so that there's a 5.0 amps over here. Once again, this cancels out. We're left with, on our left side, RT is equal to 12.5 volts over 5.0 amps. I know that was multiple steps. Just remember that this can also be represented as resistance is equal to volt over current, and this is the same way that we're getting to what we have down here with RT 12.5 over 5A. We know that the end will be in units of ohms. Now all we have to do is use our calculator to solve for the number and go and pull it out. Here we go. 12.5 divided by 5 gives us 2.5 amps of current. 2.5 ohms of resistance, I should say. My apologies. This is our RT, what we're going to be using to solve for the total resistance. What I mean by that, once again, is that we have a fraction. We have 1 over the resistance total equaling 1 over 2.5, right? This will equal a number of resistors, right? R1, maybe there's a second resistor, R2, maybe there's a third resistor, R3. We're not super sure. All we know is that once we add all of these together, this should give us the same numerical value of 1 over 2.5 over here, right? And it is not just a matter of adding R1 plus R2, what have you. And let me just prove this through an example. Let's say you have a quarter, right? Quarter of a dollar, and I give you another quarter of a dollar, right? Shouldn't this just equal, well, the sum, right? 4 plus 4 is equal to 8. Does giving you 2 quarters give you an eighth of a dollar, right? A number that we can't even represent through our money. It should instead give you 1/2 of a dollar. 2 quarters, 50 cents, 1/2, right? So 1/4 plus 1/4 will not just automatically give you 1/8. This right here is not the way to solve it. What we're going to be doing is instead using a more mathematically correct way of solving for the missing R1s in this case. So we know that on our left side, this should equal 1/2.5, and on the right side, we have 1 plus our first resistor plus 1 over our second resistor plus 1 over our third resistor. In this case, we don't know how many resistors there are. We do know, however, that there are all 10 ohm resistors. So I'm going to go ahead and write this in here as well. 10 ohm over here plus 1 over 10 ohm over here plus 1 over 10 ohm. And once again, we're trying to figure out how many of these equal the 1/2.5, right? And in this case, we kind of have to be really clear about what this 1/2.5 equals. I'm gonna go ahead and just use my calculator one more time to look at this kind of complicated, weird number in a simpler way. 1/2.5 is the same thing mathematically as 1 divided by 2.5, which is 0.4. 0.4 is what all of these different resistors should add to. So with this in mind, all of these resistors might add to 0.4. We recognize, for example, that 1 plus 1 plus 1 in this case should give us, if we're just looking at the 3, right? Let's just look at the 3. 1 plus 1 plus 1. We're adding the numerators, not the denominators. The denominators stay the same. 3 over 10, which is the same thing as 0.3. We're not quite there yet, right? So let's go ahead and keep adding one more resistor. In this case, 1 over 10 ohm. Each resistor is 10 ohm. 1 over 10 ohm. Each resistor is 10 resistance. Let's add one more because 3 times did not work last time. 1 plus 1 plus 1 plus 1 should give us 4 over 10, which should generate a 0.4. And in this case, we have 4 resistors. 4 resistors should that give us 4 over 10 ohms, right? The resistance being the denominator, which equals this 1/2.5. This kind of solving for it, let's write it in a more simpler manner. 1 over RT, which in this case was 1/2.5, is the same thing numerically as 4 over 10 ohm resistors. This relationship is what gets us connecting each individual resistor's contribution to the total resistance. The total resistance, which once again, we use to solve with Ohm's law as normal, right? As we would solve for any simple current model. That's how you get RT. And of course, sometimes you might have to work around different numbers. If there are requests to look at, for example, problem number 6 for this, because we are using not just a 10 as a denominator for the R's, right? We might sometimes use different numbers and we have to kind of solve for it. Just remember, right? Be really clear about your fractions. You do not add the denominators. You instead add the numerators and make sure that the denominators stay the same, right? In both of these cases. And once again, 1/2.5, you typically have to think about this in a different way because it doesn't really solve really nicely for other numbers. Decimals usually work and are a quick way to just figure out that both sides of the equation are in fact equal. I hope that's a little clear as to how to solve for these different problems, again with parallel resistors. This relationship being just an add-on to our Ohm's law, which still relates all of the 3 main components, the total components. But of course, any other questions, just let me know. I'm more than happy to cover other examples.